Electrodynamics Introduction to. So I'm going over this as part of my playlist linked down below. Let's get into it. We're going in chapter 1, which is just vector operations. I already talked about the scalar product, the dot product, the cross product, and basic vector operations. But now we're going to get into 3 vector operators that deal with derivatives. And those 3 are the gradient, the divergence, and the curl. Today, in this video, we're just going to talk about the gradient. Okay. So these all depend on a vector operator called, I call it the del operator. And it looks like this in Cartesian. So it has an XYZ component. This is the Cartesian version of that, just to let you know. If you use in quantum mechanics, you'll see something like this in spherical coordinates for the hydrogen atom. It gets a lot more complicated. It's easier in Cartesian. Okay. So you may also write this. I'll write this in the other format. The partial with respect to x hat, plus the partial with respect to y hat, plus the partial with respect to z hat. So that's our operator, the del operator. Now, if you remember, we had 3 vector operations that we can think of. We have a scalar times a vector. We have the dot product. And we have the cross product. Well, these are all vector operations, and that's a vector operator. So couldn't we use that on things? So could we use this on a scalar function? We can. So if I have some scalar function f, I could take del operated on f. We write it this way because it makes more sense. And this is the gradient. Gradient. It's hard to spell when you're on the board. If I take the dot product and with the del operator, I get del dot A. And this is the divergence. If I take the cross product, I get del cross A, and this is the curl. So we're not going to talk about these 2 today. Those will be in another video. So we're going to just talk about the gradient today. So the gradient says take a vector function and then operate it on this. Let's just go ahead and do an example. This is a problem from the book. But suppose that we have, I'm going to do 2 problems, and then we're going to do it numerically in Python. You know, like Python. So suppose I have a function, a scalar function f, x, y, z. So that means it has an x, y, z value, but it returns a scalar. So the one they have in the book is x squared, y cubed, z to the 4th. Let's find the gradient, and then I'll tell you how to interpret the gradient. So the gradient of f is going to be equal to the vector. I'm going to take the partial of this with respect to x as my x component. So right here, the partial of this with respect to x is just going to be 2x y cubed z to the 4th. Remember, when we take the partial, we treat the other variables as though they were constant. So y cubed and z cubed are just z to the 4th are just constants. Now for the y component, I take the partial with respect to y. So I'm going to get a 3 x squared y squared z to the 4th, power rule, right? And then for the z, I get 4 x squared y cubed z cubed. And that's my vector function for the gradient. But what does it tell me? Well, imagine the easiest way to think about this, when you think about gradients, you should think about hills, right? So imagine I have a hill that looks like this. These are contour lines. So these show lines of constant elevation. So if we're looking at this from the top, this is the highest point of the hill, and then it slopes off this way and slopes off that way. But over here, the lines are closer together, so it's steeper. So if I find the gradient at some point right here, we could represent that as a vector, and it shows me the direction that the slope is changing and how much. So it's going uphill, right? And if I did it over here, I'd have a much larger vector because it's steeper. So it tells me kind of like what the hill looks like, the slope of the hill. Next problem. Suppose that we have a surface, a hill, and we have a function for that hill. And this is the one they give in the book. I have to write it down because it's kind of crazy. So it looks like this. H as a function of x and y. And yes, there is a z component. They're just all 0. 10 times, I got to take off my glasses, 2xy to y minus 3, I don't know why they made this so complicated, 3x squared minus 4y squared minus 18x plus 28y plus 12. So the first part of this question says, where's the top of the hill? Where's the highest point? Well, if I look at the hill from the side, the highest point's up here, but where the slope is 0. And so really we're going to say, where is the gradient of h equal to 0? And remember, that's a 0 vector. Okay, because it's not just 0 in the x direction, it's 0 in the y direction, it's 0 in the z direction. So we have to set it equal to all three of those. So let's take the gradient of this and set it equal to 0. I'm actually going to say 10 times the gradient of h. Because I have that 10 right there, I don't want to deal with it. So I can just multiply this by, I can factor that out of the derivative because it's a constant. And then we're going to set this equal to 0 so the 10 doesn't matter. Okay. So I'm going to take the partial of this with respect to x. I have right here 2y. Then I have minus 6x. And then I have minus 18. That's my x component. The y component is right here. I get 2x minus 8y plus 28. And then there is no z, so I get 0 right there. Now, if I set that equal to the 0 vector, I get a 0 component for the x direction, a 0 component for the y direction. So I get the following two equations. 2y minus 6x minus 18 equals 0, and 2x minus 8y plus 28 equals 0. Let's go ahead and solve this for y. So I get 2y equals 6x plus 18, or y is 3x plus 9. Now I can plug that in over here and solve for x. So I have 2x minus 8 times 3x plus 9 plus 28 equals 0. So that's 2x minus 24x minus 72, 8 times 9, plus 28 equals 0. So I get negative 22x minus 44 equals 0. So x is going to be equal to 44 divided by negative 22, negative 2. So I'm going to put that right here, x negative 2. So now I can go back over here. Y is going to be negative 2 times 3, which is negative 6, plus 9, so it's 3. So that's where my, that's the location of, is the video messed up? Oh well, I'm going to keep on going on. If it's messed up, let me know and I'll again redo this video. Well, how high is the hill at that highest point? I'm not going to put it in, but I would say h of negative 2, 3. And so I just put in negative 2 and 3 in this function, and I get that thing right there. And then finally, what direction is the hill? I can just put that in for my del. Okay. I want to do this. I want to do this problem in Python because I think it'll be pretty fun. Okay. So how would I find this gradient in Python numerically? Well, let's leave that function right there. Let's leave that one right there too. So here I have the gradient of h is equal to 10 times that. Yeah. Okay. Okay, so now suppose I want to do this derivative. I want to say del of h is equal to the partial of h with respect to x, the partial of h with respect to y, the partial of h with respect to z. So how do you take partial derivatives numerically? Imagine I have actual numerical data. Well, this is just a derivative. If you go back to your original definition of a derivative, I can say the partial of h with respect to x is going to be equal to h, and I'm going to write it out the full way, h of x plus delta x y minus h of x minus delta x of y over 2 delta x. Right? So this says if I have some function h as a function of x, and it goes like this, I'm going to say, well, if I want to find the derivative there, I'm going to go back and forth a little bit, delta x, and then find the slope between those two, and that would give me my derivative. So I'm going to add a little bit for my function h, and then I'm going to subtract a little bit from x for my function h, and then divide by 2 delta x. And that's going to be my x component. For my y component, I'm going to say the partial of h with respect to y is going to be h of x y plus delta y minus h of x y minus delta y over 2 delta y. It's over 2, right, because I have 2 intervals on my horizontal axis. So I have to do this numerically. So I'm not going to get a function for it, but I can get a numerical value. And then we can compare that to the numerical value right there too. Okay, I do remember I said x was -2, y is 3 was my answer, because we're going to check that. Let's jump over here to Python and code this up. It's going to be fun. Now I'm going to do this in a weird way. I'm going to do this some weird functions here, but let's just go ahead and define a function. Define a function for h. Okay. So I'm going to say def h of xt, yt, zt. So I like to use the t's there because these are temporary values I'm going to pass to the function, and in the function I'm going to use xt, yt, zt. And then I can return the height. Okay. So let's say I'm just going to return it in one fell swoop. Return. Now I just need to type in my equation right here, which I have right here. It's 10 times 2 times xt times yt minus 3 times xt squared. Remember in Python, raised to the power is star star. Minus 4 times yt squared minus 18 times xt plus 28 times yt plus 12. So we can just go over here and then say print h of -2, 3, 0. That was our point anyway, just to see if it works. And so that's the highest point, is 720 units, whatever the units they had. Okay, so it looks like it's working. Now we're going to define our gradient function. And this is going to use, I'm going to give it an xyz coordinate. I can't calculate it everywhere. I'm going to give it an xyz coordinate. And then from those xyz coordinates, I'm going to get the derivative, the gradient. Okay, so I only get a numerical value, a numerical vector at that place. If I want to find it everywhere, I just have to plot it. So this isn't the same thing as taking the derivatives. It's a numerical derivative. So I'm going to call this def grad h. And I'm going to say grad h because I am using that function h, the global function. I'm not going to redefine it. But I am going to pass to it x, y, ty, zy. I have to give it some coordinates to find the location of that. Okay, so I need my dx. I'm going to say 0.001, dy is 0.001. You could just say ds. dz is 0.001. So that's how much I'm going to move back and forth in order to find these things. And now let's calculate the derivative, the slope in the x direction. I'm going to call that dfx, and it's just going to be the equation I had up there. So I'm going to say h of xt plus dx yt zt minus h of xt minus dx yt zt. And all of that divided by 2 times dx. But you can't see that. Okay, so that's that same equation I have on the board. It's just a finite difference version of the derivative. Now I need to do the same thing for the y and the z direction. I can just copy this, right? I don't need to redo it. I can copy this and then go down here. And then I'm just going to change this to y. And then right here I'm going to say minus dy. I'm going to get rid of the x. And then over here I'm going to say plus dy. I'm going to get rid of the x. And then I'm going to call this dfy. You see how that works? And then I'm going to do it again. And I'm going to change this to z. And then I'm going to say minus dz. And then I'm going to go over here and I'm going to get rid of this. And then I'm going to say plus dz. And then I'm going to get rid of this. Now I have my changes in the x, y, and z direction. I can return the vector dfx, dfy, dfz, and that's that. So if I want to, I can print the gradient. We said the highest point was at x equals negative 2, 3. So let's just print out the gradient there and see if that does indeed work. I'm just going to print grad h at x equals negative 2, y equals 3, z equals 0. And let's see what we get. Nothing. dfz is not defined. I didn't change that one. My mistake. And you'll notice it's not 0. But it's 0, right? It's a numerical derivative. So we didn't really get an actual answer. But 10 to the negative 11th is basically 0. Okay, let's just do the following, just because it's kind of cool. Suppose I didn't know the answer. How would I find the answer? Well, I could vary the value of x from, let's say, negative 4 to positive 4 and see where it crosses 0. And I could do the same thing for y. So let's make a graph. So over here, I'm going to make a graph. G1 is equal to graph. Title equals hill. X title equals x comma y. I'm going to plot both of them. And then the y title is going to be equal to dh, the slope. And let's say width, 400, height, 200. And then I'm going to make 2 graphs. I'm going to call it fx. No, call it f1. f1 is g curve, color equals color.blue. And this will be my x values. And then I'll do the same thing for y. f2 is g curve, color equals color dot red. And, ooh, why did it do that? I missed a parenthesis somewhere. X title, parenthesis. Okay, well, I'm scared. Oh, it did it that time. Okay. So now let's say x is negative 4 and dx is 0.01. I don't need the big of a step. And let's say y is equal to 0. It can matter the value of x and y. In this case, it doesn't. But it could be you couldn't just vary the x and find the maximum height for the x. That doesn't always happen. But we'll do it anyway. So while x is less than 4, I want to plot the x component of the gradient. So f1.plot grad h of x, y, 0 dot x, right? Because remember, gradient returns a vector, and I only want the x component. But that's what I want on the y-axis, so I want x, comma. And now I'm going to increment my value of x. And so this will only do the x one first. Let's just see if we get the right answer here. Okay, so I'm looking where the intercept is 0 right here, and we get negative 3. You can't even see that. Negative 3 right there. Good. Now let's do the y one. Same thing. I'm going to set x equals 0. And then I'm going to say while y, and y is negative 4. while y, oh, and then dy, 0.01. While y is less than 4, f2 dot plot y grad h x y 0 dot y. I want the y component now. And then I'm going to increment my y value, y equals y plus dy. And now we're looking at the red curve. Where does this cross 0? And it's over here. Something happened. Let's see. So I said y was 3, but I'm not getting 3. So I must have an error up here or here. dy. Let's put this at x is equal to -3. See if that fixes it. Because I already knew the location. Yep. No, it's close. It's close enough. Okay. So it does matter what you can't just vary y and get the right answer. You have to know, you have to vary both y and x. So it's not a trivial problem. Numerically, it's a cool problem, but it's not a trivial problem. So we found the top of the hill. We found the slope. I printed that. We want to find the magnitude of the slope and the direction. That's pretty easy to do too. Let's just do that real quick. At the highest point, I'm going to print dh is equal to grad h at x equals -2, y equals 3, 0. And then let's print the magnitude of that. All right, dh, which is the steepness. I mean, we already have that, really. It's just the mag of that. Remember, that is a built-in function in Web v Python. And then finally, let's print the direction dh hat. And that's just using norm, also another built-in function. And there you go. So the slope is 0 at that point, right? Like we said. This doesn't really actually matter because the slope's 0. The question asks for the slope at another point, but I'm not going to do that. So there you go. I'll give you this code, a link to this code down below. Playlist for the whole playlist for electrodynamics is also down below. The next video will be on the diversions. See you there.